Hello everyone, welcome to my video presentation on my internal defense. Before I start my presentation, I want to thank all jury members. Thank you for being part of my juries and taking time to read my thesis and follow this presentation. The title of my presentation is Automatic Detection of Appropriate Solution Methods for the Resource Constraint Project Scheduling Problem for Machine Learning. The outline of my thesis is given below. In the first chapter, I will introduce basic concepts and our 4 research questions. In the following 4 chapters, I will present our different studies which correspond to our 4 research questions. This is the relation between different chapters. In the last chapter, I will conclude our results and give a recommendation for future research. Resource Constraint Project Scheduling Problem is a classic problem formulation for project scheduling. Various project indicators are proposed to describe this problem, including the number of activity, network indicators, and the resource indicators. In order to solve this NP-hard problem, a lot of solution methods are proposed, including priority rules, branch and bound procedures, and meta-heuristics. Machine learning is a branch of artificial intelligence, which is based on the idea that a computer can learn from historical data. Multi-label classification and label ranking are 2 commonly used tasks in machine learning. However, for a project manager, it is very difficult to select appropriate solution methods for their project to generate better performance. This is also the motivation of our research. In our study, we will fill this research gap by answering 4 research questions. In the first research question, we will build a classification model to learn the relation between project indicators and the performance of priority rules. The goal is to detect the best performing priority rule for projects. In the second research question, we will rely on classification model to build the relation between project indicators and the performance of branch and bound procedures. However, in this study, we will consider the possible correlation between procedures. In the third research question, we will rely on label ranking model to find the relation between project indicators and the full ranking list of branch and bound procedures. In the last research question, we will show how to extend both classification and ranking model to different solution methods and different scheduling problems. The basic version of the resource constraint project scheduling problem assumes a single project contains a number of activities. This activity should be scheduled in order to finish the project as soon as possible. For each activity, it contains a finish to start precedence relations with time lag of 0, and once this activity starts, it cannot be interrupted until it is finished. Each activity relies on a set of renewable resources, and their availability is constrained. Each activity should satisfy with precedence constraint and resource constraints. The goal is to find a schedule that minimizes the total project duration, known as the project mixspan. Here is a simple example for RCPSP. This number indicates the ID of activity, this number indicates the duration, and this number indicates the resource requirements. Machine learning enables the computer to learn from historical data and use the knowledge obtained to predict future outcomes. Different instances form a dataset. An instance is described by a set of characteristics. The characteristics that are used to describe the instance named features. the outcomes of an instance named labels. Multi-label classification is aimed to learn the relation between features and a set of relevant labels. The goal is to predict a set of relevant labels for an unseen instance. In label ranking, it's aimed to build the relation between the features and a full ranking list of labels. The goal is to predict a full ranking list of labels for an unseen instance. In order to have a better understanding of our two machine learning tasks, here I will give an example. In this example, the number of instances is 3, and the number of features and the number of labels are also 3. Each number below the feature indicates the feature value, and each number below labels indicates the mixed span generated by each specific label. And after compare the results generated by different labels, we can obtain the best found mixed span for each project instance. And the multi-label classification data is also obtained based on the best found mixed span. We will compare the mixed span generated by each label and this best found mixed span. If they are equal, we will give a value best, otherwise we will assign no. After compare this for all project instances in the data, we will obtain our multi-label classification data. However, for label ranking, we will not only compare this with the best found mixed span, we will compare the results given by different labels. For example, this ranking list is L2, L3, and L1. We can see the L2 and L3 hold a smaller position in the ranking list. This is because the label 2 and the label 3 can generate the best found mixed span, and their tiebreaker is based on their ID number. The title of Chapter 2 is Automatic Detection of the Best Performing Priority Rule for the Resource Constraint Project Scheduling Problem. In this chapter, we will answer the first research question. And we aim to build the classification model to find the relation between project indicators and the performance of priority rules. More specifically, in order to deal with multi-label classification tasks, we will use the binary relevance method and the multi-class methods. Binary relevance assumes that the labels are independent of each other, and it transforms the label ranking learning tasks into multi-label independent binary classification tasks. Here I will continue use the multi-label classification data we already present in Chapter 1. Since the number of labels is 3, therefore, the BR methods will transform the original data into 3 different subsets. Each subset will generate for each single label. However, for multi-class, it transforms the multi-label learning task into single-label classification by defining new classes. From this example, we can see that there only have 1 column. This column indicates the new defined classes. For example, in this project instance, the new class is capital C to L2 and L3. Capital C indicates the class, number 2 indicates the number of labels that can generate the best found mixed span. And the L2 and L3 is the detailed information about these 2 labels. Here is our machine learning framework. First, we have to collect our data, then to conduct pre-processing for our data. After we finish these steps, we will divide our data into 3 different subsets. The first set is the training set, which used to build the relation between project indicators and the performance of priority rules. Once this relation obtained, we will use different parameters on validation set to obtain the best parameter settings of the model. Once these steps are finished, we will input the test set into our model to obtain the final performance of the model. In order to evaluate the performance of our model, we have conduct 3 experiments. In the first experiment, we will compare the performance of binary relevance methods and multi-class methods. The results show that these 2 methods can generate better results than any single priority rules. And G48MC has a slight advantage over G48ML has a slight advantage over G48MC. In the second experiment, we will verify the impact of label space reduction. The results show that the models are competitive when the performance of the priority rules used changes. In the third experiment, we will further examine the impact of priority rules performance. The results show that the classification model still performs best when the performance of priority rules is diverse. The title of Chapter 3 is Comparison of 2 problem transformation based methods in detecting the best performing branch and bound procedures for the RCPSP. In this chapter, we aim to answer the second research question by building classification model to find the relation between project indicators and the performance of branch and bound. Different from the method used in the chapter 2, here we will consider the possible correlation between labels. Classifier chains are used to deal with our multi-label classification task. It will assume that there are the possible correlation between labels, and it transforms the multi-label learning task into a chain of binary classification tasks. More specifically, 3 scenarios are proposed to determine the order of labels in this chain. Here I will use the example to explain CC methods. This is our original multi-label classification data present in Chapter 1, and this transformation also based on the scenarios 1. Since the number of labels is 3, therefore the CC methods will divide the original data into 3 different subsets. Each subset will generate for each single label. However, from the second and the third subset, we can see the second they consider the information of different labels. For example, in the second subset, we can see the feature space are extended by consider the information of label 1. However, for the third subset, we can see the feature space extend by consider the information of label 1 and label 2. Therefore, the label information are considered by different models. Here is our machine learning framework. First, we also have to collect our data, and then we will use the classifier chains method to deal with our original data, and then we will continue to perform data splitting, model training, and model testing. In order to evaluate the effectiveness of the model, we have performed 5 experiments. In the first experiment, we will compare binary relevance method with classifier chain methods. We will see whether consider the possible correlation between labels will work. The results show that the combination of classifier chains and the backpropagation neural network performs best. And in the second experiment, we will compare the model with each individual configuration. The results also show that the classification model can generate better results than any single configuration. In the third experiment, we will examine the impact of label correlation and the label restriction. The results show that the performance of model can be improved by considering the label correlation, and the classifier chance is competitive when the number of positive labels is restricted. In the fourth experiment, we continue to evaluate the robustness of the classifier chains on subsets with different size, and the results show that the classification model are still robust despite the number of activity changes. In the last experiment, the results show that the classification model can improve the quality of the branch and bound procedures from the literature. The title of Chapter 4 is Prediction Model for Ranking Branch and Bound Procedures for the Resource Constraint Project Scheduling Program. In this chapter, we will answer the third research question by building label ranking model. This model will be used to learn the relation between project indicators and the full ranking list of branch and bound procedures. Here is the original label ranking data we already present in Chapter 1. So our goal is to learn the mapping between features and the full ranking list of labels. However, it's very difficult to build their relation directly. Therefore, we borrow the idea of this work to mapping the ranking list into a lemma code in Hilbert space. Then our model will learn the relation between features and the lemma code in Hilbert space. After we obtain this relation for a given feature vector, we can generate prediction lemma code in Hilbert space. Then we will perform decoding process to obtain the ranking list of labels in the original label space. Here is our machine learning framework. First, we also have to collect our data. However, here we have to transform our data into label ranking tasks, and then we will continue to split our data and to select the best performing our data. Then we will evaluate the final performance of the model on test sets. Different from the classification task used in Chapter 2 and Chapter 3, here our model will generate a full ranking list of configurations instead of just a prediction whether solution methods can generate best mixed span or not. In order to evaluate the performance of the ranking model, here we have 5 experiments. In the first experiment, we will verify the impact of time limits, and the results show the model performs best under 16 seconds time limits for both training and testing. In the second experiment, we will further examine the overall performance of the model, and the results show that the models performed better than any single branch and bound procedures. In the third experiment, we will further verify the impact of performance groups. The results show that the ranking models are competitive when the performance of branch and bound procedures in the group changed. In the fourth experiment, we evaluate the robustness of the model on subsets, and the results show that the model performs best when the number of activity and the hardness of a problem instance changes. In the last experiment, we will examine the generalization ability of a model by splitting time limits. And the results show that the quality of solution can be improved by the ranking model in a time limit of 1 hour. The title of Chapter 5 is Extension of Classification and Ranking Models to Resource Constraint Single and Multi-Project Scheduling Program. In this chapter, we will answer the fourth research question. For our extension contains 2 parts. The first part extends our model in the RCPSP. Since we will extend our model in the same scheduling programs, so the project indicators that used to describe the problem is the same. Therefore, only the labels need to be redefined. However, for extension in the resource-constrained multi-project scheduling problem, since the problem is different, therefore, the project indicators that used to describe the instance and the solution methods used are different. Therefore, the features and the labels need to be redefined. The resource-constrained multi-project scheduling problem contains a set of projects instead of only one project. And these projects have to be scheduled in order to finish this whole project. And each project contains a set of activity, and these activities are interrelated by precedence and resource constraints. Each project can be treated as an individual RCPSP. However, the resource can be shared between different projects. The goal is to find a schedule for activities, take into account precedence constraint and resource availabilities to optimize performance measures. For example, we can minimizing the total portfolio mix by minimize the average project delay. In order to highlight the difference between the current chapter and the previous chapters, here I will give a summary. In this table, we can notice that in the current chapter, we consider two different problems. They are RCPSP and RCMPSP. And we will use the solution method, priority rules, and the branch and bound to solve this problem. However, we will use priority rules and the metaheuristic to solve multi-project scheduling problem. For different problems, both classification and the ranking model are used. Here we have 4 experiments to test the performance of the model. In the first and second experiment, we will compare our classification model built based on the multi-class binary relevance and classifier change methods, and then we will compare different classification model and ranking model on priority rules or branch and bound procedures. For the third experiment and the fourth experiment, we will compare these two machine learning models for priority rules and meta-heuristics. Therefore, after we compare on different solution methods, we will know in which case we should use which machine learning models. In chapter 6, we will conclude our results and give a recommendation for future research. In the first research question, our results show that the relation between project indicators and the performance of priority rules can be learned by classification models. And both classification models can be used to detect the best performing priority rules for the resource constraint project scheduling problem. And if one prefers to get only one priority rule, multi-class can be used. However, if one prefers to get high quality, binary relevance methods can be used. In the second research question, our results show that there are correlations between branch and bound procedures, and the performance of the model can be improved by consider label correlations. In the third research question, the results show that there are preference information between branch and bound procedures, and the performance of the procedures can be improved by our more ranking models. In the last research question, we know that for extensions, our classification and ranking model in the same scheduling programs, since the projected indicators are the same, therefore we only need to redefine the labels. However, for extension, our ranking model in different scheduling programs, both features and the labels need to be redefined. For our future work, we will have 3 extensions. The first extension will aim to extend our classification and ranking model to solve empirical data. We can also extend the auto model to solve different scheduling problems. For example, we can extend to solve a multi-mode version of the resource constraint project scheduling problem. We can also extend the model to solve multi-scaled resource constraint project scheduling problem. For the second extension, we can try to find a more machine learning method to solve our learning task. For example, we can try other problem transformation method. We can also use the algorithm adaptation method to solve our tasks. The last extension we can focus on to explore more machine learning topics to solve our scheduling problem. For example, we can try to make transfer to make reinforcement learning to solve our project scheduling problem. We can also use deep learning to solve our problem. Thank you for your attention. I'm looking forward to your questions and comments.